So I hope the PDF is visible to you. So this is the clause 26.5.3 regarding columns in our IS 456, and in that we have the subclause that is longitudinal reinforcement. So these are the conditions regarding the longitudinal reinforcement, and we should ensure that we are adhering to these conditions. So let's see what are the different conditions that code suggests. The cross-sectional area of longitudinal reinforcement shall be not less than 0.8 percentage nor more than 6 percentage of gross cross-sectional area of the column. So what do you mean by that? So basically, if we have a column, say let's take the cross-section as a rectangle, we will be providing some reinforcement in that. We will be having some main reinforcement in that. And when we take the ratio of this main cross-section of this main reinforcement to the total gross cross-section, this ratio should not be, or this area of steel should not be less than 0.8 percentage. Okay, so at least we have to provide 0.8 percentage of the total cross-sectional area. And one more thing is there, upper limit is also there, that is we cannot provide an area of steel greater than 6 percentage. What will happen if we are providing, say I am going to provide 8 percentage of steel? It is actually better, right? So steel is very good in taking up compression as well as tension. So what is the problem in providing a percentage above 6%? What can be the reason for that? Can someone suggest me what can be the reason for that?
Sir, economy.
Economy is a factor, okay. Then anything else? That is not the major thing. Yes?
While pouring the concrete into it, it might not get evenly compacted in between.
Exactly correct. Exactly correct. So if suppose you please visualize, we are providing a large number of longitudinal bars. Say we are providing a higher percentage of steel area, and so we will be resulting with a large number of bars. So what will happen? See, basically columns. If you have seen the casting of a column, we will be providing the shutters on all the sides, and after that we will be pouring the concrete from the top. Okay, so we cannot ensure that this concrete will be properly reaching all the positions. So what will happen? There will be a lot of congestions since there is a presence of large number of bars. So we cannot ensure that we will get proper compaction for the concrete. We cannot ensure that the concrete will be reaching each and every corner inside the shutter. So that is the main reason why we restrict the amount, maximum percentage of steel to 6 percentage. Okay, so that's it. And again, this is a question that is usually asked for competitive examinations. So they may be asking what is the maximum amount percentage of steel permitted for column, or what is the minimum steel area that should be provided in a column. So you can expect such questions. Then one note is given. Let's see what is that. The use of 6 percentage reinforcement may involve practical difficulties in placing and compacting of concrete. Again, what we have already discussed, even 6 percentage is not that recommended. Hence, lower percentage is recommended, where bars from the columns below have to be lapped with those in the columns under consideration. The percentage of steel shall usually not exceed 4 percentage. That is, you say, let's take an example of I am going to construct a 20-story building. Okay, my structure is having 20 stories. So can I get a single reinforcement which can run from the bottom of this structure to the top of the structure? No, we won't be getting that. We will be getting standard length. So what will happen? So what we should do is that we have to actually provide laps. We will be keeping one bar over the other and we will be tying it. So in case in a column we are having laps, what is the recommendation? So when we have these bars to be lapped, the maximum percentage of steel that is permitted is again reduced to 4 percentage. Okay, so please note these things. And in any columns that has a larger cross-sectional area than that required to support the load, the minimum percentage of steel shall be based on the area of concrete required to resist the direct stress and not upon the actual area. Okay, so that means suppose we have to resist a load of say PU of say 1000 kilonewtons. Okay, and I have taken a very larger section, say something like say this is by 1 meter by 1 meter, and we have some reinforcements provided here. So what this code states is that say in any column that have larger cross-sectional area than that required to support the load. So basically, we need to carry only 1000 kilonewtons, and we have provided a larger area which is more than sufficient to carry this 1000 kilonewtons. We know the compressive stress of concrete and we know the load, so we can calculate the area required for carrying that load, because stress is equal to force by area. Using that relation, we can easily calculate the minimum required amount of area to be provided. Suppose in a column which is having larger cross-sectional area than that is required to support the load, what we should do is that the minimum percentage of steel shall be based on the area of concrete required to resist the direct stress. In the previous clause, we have already mentioned that the minimum percentage is 0.8 percentage. Okay, so if we are providing a larger area than what is required, this 0.8 percentage will be resulting in a larger value of in a different value of AST. That is not the right way. So what we have to do is that we have to actually find out the exact amount of area required for carrying the load, and we have to ensure that the minimum percentage is 0.8 based on that, or the maximum percentage of 6% is based on that. That is what is here they are actually focusing on the minimum percentage of steel. So in any column that has a larger cross-sectional area than that required to support the load, the minimum percentage of steel shall be based upon the area of concrete required to resist the direct stress and not upon the actual area. Okay, so that is what is mentioned in clause number B. Then moving down, we have the minimum number of longitudinal bars provided in a column shall be 4 in rectangular columns and 6 in circular column. Again, a repeated question for your competitive examinations. Normally, they will be asking about this circular column. So, what is the minimum number of bars that should be provided in a circular column? That is 6. If we are taking a circular cross section, we have to ensure that at least we are providing 6 number of longitudinal bars. Whatever the area requirement, we have to actually provide 6 number of longitudinal bars, and if it is a rectangular shaped column or a square column, we have to at least provide 4 number of longitudinal bars. That is the minimum requirement suggested by IS 436. Then what else? Then the bar shall not be less than 12 millimeters in diameter. Okay, so basically when we provide the longitudinal bars, the minimum diameter of bars required is 12 millimeters. Again, this can be expected for your competitive examination. Anyway, this is repeated more times. That is regarding the minimum number of reinforcement that should be provided in circular column, as well as this percentage of maximum percentage of steel that have to be provided in column. Those things are usually repeated things. Again, this you can expect for some interviews. The bars shall not be less than 12 millimeter in diameter. That is the minimum diameter of bar that should be provided as a longitudinal bar in the case of our columns. Then in the next clause we have a reinforced concrete column having helical reinforcement shall have at least 6 bars of longitudinal reinforcement within the helical reinforcement. I hope I have already shown you the figure of helical reinforcement. We will be providing the ties in the form of a spiral. So basically we will be having a lot of vertical longitudinal reinforcement, and around this we will be providing ties in the shape of a spiral. Okay, so that is more effective actually. So we will see the details of that in a later stage. Anyway, in a helical reinforced column, the longitudinal bars shall be in contact with the helical reinforcement, and sorry, we were discussing about this one, right? So basically what this says is that we have to, when we provide spiral ties, we have to at least provide 6 bars. That is what is mentioned here. Then again in the same thing, in a helically reinforced column, the longitudinal bars shall be in contact with the helical reinforcement and equally distant around its inner circumference. So you can directly understand that basically we have to keep the distance between these bars equal, and it should be in proper contact with the helical reinforcement. Then spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 millimeters. I hope things are directly clear for you. So when we provide, if we are providing 4 bars, the minimum distance or the maximum distance that can be provided between 2 longitudinal bars is 300 millimeters. Okay, so basically if we have a cross section like this, say suppose I have a cross section like this, okay, and this is say 250 millimeters, and this value is something, say a special type of column, so this value is 750. Okay, So in this, can I provide reinforcement like this? In this fashion? No, we cannot. As per this clause, we cannot provide like this because this code clearly mentioned that the spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 millimeters. So this distance will be somewhere around maybe 700. So we cannot provide like that. So we have to go to a maximum distance of 300, after which we have to provide at least one longitudinal reinforcement like this. So here also we have to provide it like that. So this thing actually comes from this restriction as per our IS code. Spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 millimeters. Next one, in case of pedestals in which the longitudinal reinforcement is not taken into account in the strength calculation. That is okay. That comes when we design the foundation and all. Pedestals are small columns normally provided in the foundation. Anyway, we will neglect that now for the time being. Now moving on to, till now we have discussed about the longitudinal reinforcement. So if you see here, we were discussing about the main reinforcement that we should provide in the column and what are the restrictions, what are the maximum percentage of steel that can be provided, what is the minimum percentage, what is the minimum diameter, and what is the minimum number of bars provided in circular column as well as rectangular columns, and some more details we have already seen that. Okay, so what we have to right now focus is regarding the pitch and diameter of the ties. So basically when we provide the transverse reinforcement, we have to ensure that the distance between these ties are actually satisfying the minimum criteria. So that is what we call as pitch, that is center to center distance between the ties. And also the details regarding the diameter of the ties is explained here. So we will first look into the details for the pitch. So once we finalize the diameter and the center to center distance of the ties, and we have to ensure that the provided center to center distance is satisfying these conditions. So what is the condition? The pitch of transverse reinforcement shall be not more than the least of the following distance. As usual, we have three conditions. The least lateral dimension of the compression member. So basically when we have a compression member like this, we have to ensure that the center to center distance is not less than the smaller of these two directions. Okay, that is the first thing. Then 16 times the smallest diameter of the longitudinal reinforcement bar to be tied. 16 times the smallest diameter. So suppose we have a larger column like this, and in the corners I have provided 16 millimeter diameter bars, and here I have some 12 millimeter diameter bars. So this is basically 12 mm5, and this is basically 16 millimeter 5. So in this case, as per the second condition, what I have to take care is the smallest diameter, that is 12 millimeters. That multiplied by 16 times the smallest diameter of the longitudinal reinforcement bar to be tied. So this quantity should be found out, and first one is the least lateral dimension should be found out, then 16 times the smallest diameter should be found out, and we have a numerical quantity that is 300 millimeter. And the smallest value among these three should be taken and should be compared with the center to center distance that we are going to provide between the ties. Okay, this is one condition regarding the pitch. Then regarding the diameter, we have the diameter of the polygonal links or lateral ties shall be not less than 1/4 of the diameter of the largest longitudinal bar, or in no case less than, it is not 16 millimeters actually, 61.6. It may be 16 millimeters, not less than, in no case less than. There is some correction here, not 16, the diameter of the largest longitudinal bar, in no case less than. This is wrong actually. So you please visualize, we cannot use 16 mm bars for tying as ties. Okay, I will give you the corrected value. There is some correction here. This is not 16 mm. Okay, anyway, the diameter of the polygonal links or lateral ties shall not be less than 1/4 of the diameter of the largest longitudinal bar. So if you take the same example, here we were having 16 millimeter 5 bars and 12 mm 5 bars. So when we provide the diameter of the ties shall not be less than 1/4. That is, in our case, 16/4. We cannot provide the diameter of the polygon tie shall not be less than that. We have to provide a tie which is having a diameter larger than that value. Okay, so these are the conditions regarding the pitch and diameter of your ties. And regarding helical reinforcement also, they have provided some clauses. Anyway, while doing the problem, we will come back to this clause. This thing is actually somewhat slightly confusing. Anyway, we will discuss that in detail. So at that time, I will come back to this clause, helical reinforcement. Okay, so any doubts till now? Now let's do one thing. Let's see how to design a column. Okay, so please understand that as per your syllabus, you have only axially loaded columns. We have two types of columns, and in practical case, it is very difficult to get axially loaded columns. Okay, so now all of you please listen here. So basically, it is very difficult to actually. What do you mean by axially loaded? If we have a column cross section like this, we have to actually put the load exactly at the axis. So that is, in practical point of view, that is not possible. So what code suggests is that we can provide a 5% variation. So take the cross section, and if the load is actually acting within this 5% variation, it can be considered as an axially loaded column. So basically, code allows a 5% variation in the position of the load, so that it can be again considered as a axially loaded column. So in such a case, what code suggests is that we can calculate the load carrying capacity of a column as the sum of load carrying capacity of concrete and as the load carrying capacity of steel. So basically, we know that in the case of column, we will be having a piece of concrete. So this cross section is made up of concrete and steel. So as we know, the total capacity will be the sum of load carrying capacity of this concrete and this steels. So that is what is mentioned here. So, and again, code gives you an equation for calculating this load carrying capacity. Okay, and as per clause number 39.3 of page 71, the equation given for finding out the load carrying capacity is PU. This is again factored load. This is equal to 0.4 FCK into AC plus 0.67 FY into ASC. Okay, that is ASC means it is the area of steel provided. FY is the yield strength of the steel. Then we have AC as the cross section of concrete. Then we have FCK value. Let's go to the code and see this equation 39.3. Okay. So here we have short axially loaded member. So please look into this. This is what we have in our syllabus, short axially loaded members in compression. So here we have the equation PU is equal to 0.4 FCK AC plus 0.67 FI into AC. Okay. And again, if you are speaking how we are getting this equation, it is again related to this one. So in this case, we are actually providing an allowance of 5% variation, right? So what we will take is that we will actually take only 90% of this value, 90% of the load carrying capacity. That is how we are actually getting this equation. See, if you see this, what was the stress, maximum permitted stress in concrete? You have already seen the assumptions, right? The maximum compressive strain in concrete in axial compression is taken as 0.002. And again, they have mentioned that in addition to the assumptions given in 38.1, which is assumptions for flexure, right? So basically, all these assumptions, 38.1 is applicable to compression also. And in this case, they have actually mentioned that we can use this stress strain curve. This stress strain curve we are actually using for the purpose, right? So in this, you know that this is the strain and this is the stress. And if you see this, we have the strain variation. Here we have 0.002. Afterwards, we have a constant stress up to 0.0035. And in the assumption corresponding to compression, they have mentioned that the strain is, maximum compressive strain is 0.002. What is the corresponding stress for this? If we go up, this will be the corresponding stress, and we know that this value is 0.45 FCK. Okay, and since we provide a 5% allowance here, we will be taking only 90% of that value. That is the reason why we are taking only 0.9 times this 0.45 FCK. This will come around something like 0.40, some decimal values. Anyway, we will take it as 0.4. And again, when we consider mild steel, we will be having 0.75 as our instead of 0.87. In the case of mild steel, we will get the factor of safety final value as instead of 0.887, we will be getting it as 0.75, and 0.9 multiplied by that 0.75 will give you this factor, that is 0.67. Anyway, please keep this in mind. This is not needed for performing the design actually, so I was just sharing the information. Anyway, final load carrying capacity of our column will be given by this equation, which mentions that 0.4 FCK into area of concrete plus 0.67 Fy into area of steel. So this equation can be utilized for finding out the load carrying capacity of our column. Okay, then some more things are mentioned here. Let's firstly go through this also. The member shall be designed by considering the assumptions in 39.1 and the minimum eccentricity, and we will check the minimum eccentricity right now. So basically we have to consider all the assumptions as well as the condition for minimum eccentricity. When the minimum eccentricity as per this clause, so the details of minimum eccentricity is given in 25.4, does not exceed 0.05 times the lateral dimension, the member may be designed for using this equation. So we cannot always use this equation. So if we have a axially loaded column, how we can ensure that it is axially loaded? So in that case, what we do is that, as we have already mentioned, we will be providing 5% allowance for considering a column to be axially loaded. So that is what is mentioned here. When this minimum eccentricity, that eccentricity does not exceed 0.05 times the lateral dimension, 0.05, that is 5% of this distance, this lateral dimension. When the eccentricity does not exceed this 5%, we can consider that as an axially loaded column, and in that case we can use this equation. That is what is mentioned here. Don't get confused. When the minimum eccentricity does not exceed 0.05 times the lateral dimension, we can use this equation for calculating the load carrying capacity, because this equation is purely for loaded short columns. And now let's firstly see what is the minimum eccentricity as per 25.4. So if you go to 25.4, okay, here we have minimum eccentricity. So all column shall be designed for minimum eccentricity equal to the unsupported length of the column by 500. That is unsupported length of the column by 500 plus lateral dimension by 30. Okay, so this is the equation: unsupported length of the column by 500 plus lateral dimension by 30, and it should be, there is a minimum value for this, that is subjected to a minimum of 20 millimeters. Normally for the design, what we will do is that the minimum X value will be directly taken as 20. Instead of working out this, we will be directly taking 20 as the minimum eccentricity, so that this condition will be automatically satisfied. Okay. The second statement is regarding biaxial bending, that we will discuss in your DCS 2. Anyway, here what you have to notice that we will be taking the minimum eccentricity as 20 millimeters, and we will be comparing this value with 5% allowance, that is 0.05 times the least lateral dimension. So that is how we will ensure that our column is a axially loaded column.